In Part 1, we analyzed the internal structure of the atom. We looked at the protons, neutrons, and electrons, and saw how atoms gain or lose charges to become ions and radicals. Now we need to address the next mechanical challenge. How do these individual charged components bind together to form every compound in existence? Mastering the rules of chemical formulas and the architecture of the periodic table provides the framework for understanding how all matter is constructed. Every compound is represented by a chemical formula. To write one accurately, we follow a specific 4-step protocol. Step 1. Write the two parts of the compound side by side. The positive cation always goes first, followed by the negative anion. Then note the valencies, the numerical charge for each part. Step 2 is the criss-cross. Take the numeric valencies from each part, swap them, and write them as subscripts next to the opposite element. Step 3 applies when we are dealing with polyatomic ions, ions made of multiple atoms. If their exchanged valency is 2 or higher, you must enclose the entire polyatomic ion in brackets before writing the subscript. Step 4 is simplification. Divide the exchanged valencies by their highest common factor. If a subscript reduces to a 1, we leave it unwritten. Following this exact sequence prevents errors, ensuring you reach the correct chemical formula for any compound. Let's apply this sequence to iron 2 sulphide. Iron has a valency of 2, and sulfur has a valency of 2. We write them side by side, Fe and S, and crisscross the 2's to get Fe2S2. Next, we divide by the highest common factor. Since 2 divides into 2 evenly, we reduce the subscripts to 1s. Because we drop the number 1, our final formula is FeS. Now, let's build iron 3 carbonate. This combines a single iron atom, having a valency of 3, with a polyatomic carbonate ion, which has a valency with 2. Crisscrossing gives the iron a 2 and the carbonate a 3. To avoid confusion, you must lock the carbonate in brackets before adding the 3, resulting in Fe2CO3-3. We see a similar rule with calcium hydroxide. After crisscrossing, the raw formula is Ca1OH2. We remove the 1, leaving the correct formula CaOH2. Even when two polyatomic ions combine, like ammonium and sulphite, the logic holds. This yourself. Pause the video and derive the formula for ammonium sulphite. Ammonium, or NH4, has a valency of 1. Sulphite, or SO3, has a valency of 2. When you cross the valencies, the ammonium group receives the 2. Since ammonium is a polyatomic ion and the value is greater than 1, we use brackets, resulting in the formula NH42SO3. By following the crisscross and bracket rules, even long chemical names resolve through a consistent logical system. Throughout these examples, we have used valency to determine how atoms combine. By definition, valency is the combining power of a specific element. This diagram shows how we practically measure that power. We calculate an element's valency by tracking exactly how many hydrogen atoms it will combine with. Look at the structural composition of water. 2 hydrogen atoms snap to 1 oxygen atom, meaning oxygen has a valency of 2. In ammonia, 3 hydrogens attach to 1 nitrogen, giving nitrogen a valency of 3. And in nitric acid, 1 hydrogen attaches to a nitrate radical, so the nitrate radical has a valency of 1. Hydrogen provides a consistent yardstick, allowing us to physically measure the structural capacity of different elements. To see the full map of those elements, we look to the periodic table. It organizes all 118 confirmed elements in order of their increasing atomic number. The grid is structured into 18 vertical columns called groups and 7 horizontal rows called periods. Every element in the same vertical group shares the exact same number of valence electrons. Because of this, they also share similar chemical properties. This chart shows how to calculate valency directly from the table. If an element has 4 or fewer valence electrons, its valency equals that number. If it has more than 4, its valency equals 8 minus that number. In group 2, calcium and magnesium both have 2 valence electrons. Applying the rule for 4 or fewer, they both share a calculated valency of 2. The periodic table is a predictive engine for chemical reactivity. To understand why the table is so predictive, we must look inside the atom, where protons and neutrons are surrounded by orbiting electron energy shells. The total number of protons dictates the element's atomic number, while the sum of protons and neutrons determines its mass number. The outermost energy level is the valence shell. The specific electrons traveling along this outer path are the valence electrons. Because they occupy that outermost physical layer, valence electrons dictate an atom's combining power and the resulting chemical formulas. The behavior of these valence electrons dictate chemical bonds and gives the periodic table its predictive rhythm. But here is a paradox to ponder. If an atom's volume is dictated by electron orbits, leaving the structure more than 99.99% empty space, why does solid matter feel solid when you touch it, instead of your hand just passing right through? Like the video and press the subscribe button to follow our future explorations of the quantum universe.